full Rubin operations, we hope. And of course, the AGN science collaboration is in all the various AGNs, as well as broader issues of AGN evolution and AGN's relations to cosmic structures and things like that. So we're interested very broadly in all aspects of AGNs. Now, the overall goals of the AGN science collaboration are to maximize the AGN science return coming from LSST, from the LSST, to give feedback to the project to ensure excellent AGN science, and then, of course, to educate the broader community about LSST AGN science. So those are the goals that we're attempting to execute here. And the AGN Science Collaboration has, in fact, existed since fall 2006. Here's, I believe, the first email I've ever dug up that indicates that this science collaboration actually exists. This was sent by Michael Strauss back in 2006. And we have generally become more organized over time, although that's always a challenge. And one point which is quite important to be clear about is that the AGN Science Collaboration has always been, by its original design, and here is the original design document for the science collaboration, has always been distinct from the project. So we have never received direct funding from the project. We're not getting rich off this or anything like that. So this is not, you know, if you want to be rich, this is not the best approach. But it is very exciting scientifically. Okay, so in terms of membership of the AGN Science Collaboration, we currently have 215 members. We're continuing to grow rapidly. We grew by 28 people just over the past year. There are 198 associate members, and it's quite straightforward to become an associate member. And then there are 17 full and core members. These are people that have invested quite a bit of further work in making the science collaboration operate. And here is a table just showing the 6 largest national memberships. The US has 98, so it's the largest as one might expect. Membership applications are welcome, even from people who lack data rights. Now, everyone at a US institution, so that's people relevant today probably mostly, you know, are mostly probably at US institutions, and so you automatically will have data rights just by that fact. But in case you're not, there are some technical details. And just to be clear, AGN Science Collaboration membership by itself does not provide data rights. But again, for US people, that's just not an issue. And application instructions, if you have interest in joining, are available at this website. Okay. So the overall organization of the AGN Science Collaboration is shown in this plot. I believe Gordon Richards originally made the first version of this plot. We're getting ourselves properly organized. There are 2 co-chairs, myself and Mathew Temple, who's currently at the University of Durham in the UK. There are then a set of operating panels to help the various logistical aspects of the science collaboration function. And then there are sort of science subgroups based on, you know, focused on topics like AGN selection, photometric redshift, variability, follow-up, and so on. In addition to these structures, we also have a liaison to the extremely important Survey Cadence Optimization Committee, or SCOP. This is the committee that is deciding what the Rubin cadence will be. And ensuring that's good for AGN science is one of the critical things that we've been doing. That is currently Franz Bauer. I believe Roberto Assaf will soon take over that role. We also have 2 members of the Users Committee. And then we also have coordinators of international in-kind contributions. Our 2 coordinators are Sebastian Honig and Paulo Coppi. And there are 6 so-called in-kind contributions, mostly coming from Europe, and one is also coming from Canada, that are making important contributions to the AGN Science Collaboration. So that's another critical aspect of what's going on. And so international people may be interested in that in much more detail. We have a roadmap document. This is publicly available on our website. This lays out the various AGN Science Collaboration activities needed to prepare for Rubin operations. And given that operations are now rather near, work is ongoing to address many of the roadmap goals, of course. And so this document can be very useful if you want to see the definitions of the things we think are important and how they're being prioritized. And then in terms of recent and ongoing activities, we are now regularly meeting. These are photographs of the attendees of our 2 most recent science collaboration meetings. The earlier ones from 2020 to 2022 were over Zoom. We hope to have another in-person one this coming summer. The details are still being sorted out. And recordings for the full 2020 to 2024 meetings are available on YouTube. Send me an email, I can send you a YouTube playlist, and you can enjoy what we're up to for 30 plus hours now, if you really are a glutton for punishment. Okay, so then, in terms of other things that we're doing, well, we have run data challenge activities. These, motivated working on relevant data sets that will be important once Rubin begins operating. These are part of our general efforts to prepare students and postdocs and others for LSST AGN science. Monetary prizes were awarded for contributions to this, and the data challenge data set was made public. In addition, of course, as I mentioned, we're doing lots of work in the deep drilling fields. I'll talk about that in the second part of my talk, so I won't mention that here. And then we are, of course, making important contributions to getting the survey cadence right for AGN science. This is extremely important. We have delivered now 4 journal articles that are all public, which you can read if you're interested, giving our thoughts on what aspects of the cadence are important for various types of AGN science. We also have delivered 8 cadence notes. Here are the abstracts for 6 of them. These are all, again, publicly available, so you can check these out. And we also have delivered 4 coded metrics. All of these are important in giving our inputs into what aspects of what we think the cadence needs to be like to ensure that AGN science will be executed well. We continue communicating with this important survey cadence optimization committee via feedback to our liaison and the deep drilling field cadence task force. There are also regular survey cadence optimization committee workshops with the science collaborations. We provide inputs there, and the AGN Science Collaboration member continue working through new operation simulations to assess if the cadence as it's currently being planned is going to allow our desired science to be achieved. And we also coordinate with other science collaborations to see if we can push for mutually acceptable cadence solutions. For example, we've had very productive discussions with members of the important dark energy science collaboration. They're interested in supernovae, so if we can find a cadence that lets them do their supernova science, but also lets us do our AGN science, we can mutually push for a good solution there. Other key activities in 2023 and 2025, well, the AGN Science Collaboration has several members on the Rubin Euclid-derived data products working group, allowing excellent science to come from both of those missions operating together. We have 15 plus members involved in the data previews. This is getting people ready to actually work with the Rubin data when it comes. We are making updates to our charter, and currently we're making updates to our publication policies to be sure all of that is well organized and clear and logical by the time the data start to flow, so there won't be conflicts arising with people disagreeing about the various rules of the game. And we have an ongoing demographic census, and we are coordinating with other AGN projects, for example, spectroscopic reverberation mapping campaigns, or X-ray missions, to ensure that excellent joint science will be done by combining the data from these facilities together. We have also a number of relevant outreach activities. I'm personally very fond of these. We give talks worldwide to tell people about what the AGN Science Collaboration is up to. I actually run teacher workshops at Penn State where we talk about Rubin quite extensively. And then as other examples, our colleagues in Serbia have run valuable workshops for students from Ethiopia and Serbia together to help outreach Africa in this case. And there are also various other important community demo sessions and outreach events where we're making contributions. So those are some of the key activities of the AGN Science Collaboration. There's much more I could say, but that will serve as a brief summary for now. And I will now tell you about the second part of my talk, which is going to be more focused on the deep drilling fields and on our efforts to gather and analyze multi-wavelength data in the deep drilling fields to get ready for Rubin operations. And then I'll talk about some of the AGN science that will ultimately result from all this once Rubin begins operations. So Rubin's deep drilling fields are sort of illustrated in this slide. There are 5 Rubin deep drilling fields. They're shown here. These are these yellow regions in this overall operation simulation of Rubin. And in these fields, Rubin will likely observe the deep drilling fields, at least for some significant period of time, like every 2 to 3 nights is GRIZY. There also will be U-band coverage swapping in and out. And this table here lists the various deep drilling fields. And these plots shown here in the upper right show the various multi-wavelength coverage that's already sort of in the can right now for the deep drilling fields that's publicly available for people to be working on. In particular, I want to highlight that there are subregions of these deep drilling fields. Each one, of course, of these is 10 square degrees. It's the size of a Rubin field, except for this Euclid Deep Field South, which is actually going to be 20 square degrees, but at roughly sort of half depth or half cadence. And most of the multi-wavelength preparatory work, at least that I'm aware of, has been done in these 4 original deep drilling fields. This other one is coming along. Clearly it has excellent Euclid data, but gathering all the multi-wavelength data is going to be a bit of a longer haul for that one. And in these areas, where you can see the multi-wavelength data, just from these various colored shapes here, are concentrated in the central parts of these fields. Getting 10 square degree coverage with many of these multi-wavelength facilities is very challenging. And in particular, we focused a lot of efforts in these so-called SERVS regions, which were defined originally by Mark Lacey, who I believe is here. Here he is, yes. And this is the Spitzer Extragalactic Representative Volume Survey. So that's where there was superb Spitzer data to start with. There now, in fact, are Spitzer data over most of these deep drilling fields, as you can see. In fact, this grayscale in the background here is showing the Spitzer coverage for the fields. Now, examples of the multi-wavelength observational campaigns that we've done. Well, with XMM Newton, for example, we were very fortunate to be awarded a 5 million second multi-year heritage program, which has let us gather excellent quality X-ray coverage over as much of the deep drilling fields as we could manage. We couldn't get the full 10 square degrees, but we got these prime multi-wavelength regions, the best multi-wavelength regions, in Deep Field South, in Alliance S1, and in XMM LSS. There also, of course, is already, separate from our program, excellent coverage in Cosmos over a 2 square degree region. And these are the various sky coverages and the rough geometries of the coverage. So that's what we've done with XMM Newton, and that has delivered already 10,200 X-ray validated AGNs. So we already have 10,200 AGNs in the can and pretty well characterized, ready to go once Rubin operations begin. And in addition, as I mentioned, as part of the AGN science collaboration efforts, Mark Lacey led a program to get excellent Spitzer coverage of as much of the deep drilling fields as possible. And so you can see here, this grayscale again shows that we have pretty complete coverage over the 10 square degrees for Deep Field South, Elias S1, and XMM LSS. Less for Cosmos, although I believe there's been further Spitzer data gathered there later on. And so we have excellent Spitzer data in the can as well. Again, that's coming from AGN science collaboration efforts there. And just to show you an example, going back to the X-ray, here is an example of the panoramic X-ray coverage we have now all around the Chandra Deep Field South. So this down here, that's the super deep Chandra Deep Field South region where there's extraordinarily deep multi-wavelength data across the entire electromagnetic spectrum. We have now gathered wider field X-ray coverage, not nearly as deep, but still quite impressively deep, at about a 50 kilosecond XMM depth, over an area that's about 30 times or 35 times larger than just the CDF South proper, okay? And for comparison, that's the size of the moon on the sky. So this is a pretty good area of sky there, where we have excellent X-ray coverage. And most of these X-ray sources are the AGNs, although we do have interesting clusters and groups as well. The multi-wavelength data, extend just beyond the X-ray and infrared, of course. This table might be a little hard to see, but I'm highlighting here that we also have good coverage, not just with Spitzer, but out in the far infrared with Herschel, and then also in the nearer infrared with video. And then we also have, already, even before Rubin, we have some quite high quality optical data, we have some ultraviolet data, and so on. And we've been putting all of these multi-wavelength data sets together, analyzing them in sort of a systematic, uniform way. We perform tractor-based photometry, we get matched high-quality photometry, which we then use to estimate photometric redshifts and to perform fitting of spectral energy distributions. As an example of that, Fan Zhao, who is an excellent Penn State student who just recently graduated from the University of Michigan, did SED fitting for 2.8 million of sources in 3 of these deep drilling fields, running all the way from the X-ray to the far infrared. So as I said, the SEDs were uniformly extracted and fit. Here are 3 examples of SEDs for a galaxy, an AGN, and a bursting quenching galaxy. And in this case, we actually utilized the X-ray data directly in the SED fitting. And that's extremely valuable for breaking degeneracies inherent in SED fitting, where the X-rays help to lock down the level of the AGN contribution. That removes a lot of the degeneracy that comes if you have an AGN in your SED fit. And we then utilize the SEDs to perform improved source classification. That's where these classifications over here are coming from, as I've labeled, and also to perform measurement of galaxy properties. We want to know for all the AGNs, what is the stellar mass of the galaxy in which it lives? What is the star formation rate of the galaxy in which it lives? Well, for many of the AGNs, where the AGN is not too luminous, it's possible to measure those things. And as I said, we can then calibrate our stellar mass and star formation rate measurements, in this case, against the extremely deep Chandra-Deep field south. So we analyze that little region with the same quality data that we have for our full sky area back here, and we then compare the results you get for the narrow field versus the wide field. And as you can see from these plots, we do quite well, even with our shallower data, at reliably recovering stellar masses and star formation rates. So we have quite good measurements of these things already for these 10,200 AGNs, or at least most of them. As well as, and we didn't do it for only the AGNs, we also did it for all the galaxies. We fit everything in the fields down as deep as you can go with the current data. And so again, there's lots of excellent SED data available for AGNs as well as for comparison samples of galaxies there. And this can be the groundwork for huge numbers of papers in the future, we think. And we'll only get better, and we plan to do it better once the Rubin data come as well, of course. We have done other types of AGN selection, in addition to X-ray based selection and infrared selection and SED-based selection. We also want to use, for example, radio techniques to select as many AGNs as possible. This is extremely important because with radio AGN selection, you're often selecting these sort of lower luminosity kinetic mode AGNs that you do not select via the X-ray or infrared techniques quite often. And so we've utilized data from the ATLAS survey, from the DLA survey, and now from the MICHE survey to find radio AGNs. We do this by looking for radio excesses. This plot here shows that these sources over here with large radio excesses compared to what you expect from their infrared. Those are the sources we think are likely AGNs. We also utilize radio morphology, radio spectral indices, and so on to select AGNs. And as expected, we find another large population of AGNs, largely distinct from the X-ray AGNs, as you can see from the Venn diagram, selected via the radio techniques. In fact, with aggressive mining of the radio data, and this has recently been done in a paper led by a Penn State graduate student, Bo-Jun Chang, we now have found 6,666 radio AGNs selected at a pretty good level of reliability in these fields as well. And so we now have raised the AGN population in the deep drilling field already to more than 16,000 objects. And so there'll be lots and lots of great stuff to do. As soon as the Rubin data switch on, we'll be ready to go with all of these AGN data sets. We also have selected lots of other interesting individual AGN classes. I'm not going to go through these in great detail, but briefly, we have also selected highly obscured AGNs. We've utilized X-ray spectral fitting, as well as the spectral energy distributions, as well as luminosity correlations. This is an X-ray infrared luminosity correlation to select out highly obscured AGNs in these fields. And we're continuing to investigate these. This was led by Vivian Yan, who is now a professor in Iowa, so she did a very nice job on this work. We also are selecting out other interesting AGNs. There's a large population of dust-obscured galaxies in these fields, of course. There are 3,738 so-called dust-obscured galaxies, which we've selected via the standard definition, which involves looking for sources with very large 24-micron to hard-band flux ratios, and we then have utilized the X-ray multi-wavelength to define the AGN population of these objects. We've selected about 350 AGNs in these interesting dust-obscured galaxies that will, again, be interesting to study further when Rubin begins operation. We've also, just very briefly, selected AGNs in dwarf galaxies. This is another part of Fan Zhao's excellent PhD thesis. We've selected here 73 dwarf galaxies over a fairly broad range of redshift that we think are dwarf galaxy AGNs, and we've used these to measure the AGN fraction down to the lowest stellar mass as possible. Many more details, but I'm just going through the highlights here. And we also have just recently finished work, and I think this is quite exciting, setting constraints upon cosmic supermassive black hole growth by combining together our constraints from X-ray surveys, which tell us a lot about the accretion aspect, the growth by accretion, with the illustrious TNG simulations, give us a lot of excellent constraints on galaxy mergers and how black holes may be going via mergers. So we've been able to constrain the relative roles of black hole accretion as well as binary mergers in supermassive black hole growth. We find that accretion generally dominates, but that at late cosmic times, and especially for high galaxy masses, mergers there may be playing quite an important role. We also have done a lot of other things in this work. There's many technical things I can go through, but we have set what we think are the best constraints on the overall black hole mass distribution as a function of redshift. And we've identified, where all the black hole mass lies in the universe at any given redshift. There's lots of interesting results that have come out of that work as well. So all of this stuff is flowing out of these multi-wavelength constraints of the deep drilling fields. And then, just to say a few words, well, of course, once Rubin switches on, what do we plan to do with all of this? Well, there's a lot of things we plan to do. We're excited about doing accretion disk reverberation mapping via continuum lags to measure accretion disk structure well. I think Yasaman's going to talk about that in her talk. We aim to also combine multi-object spectroscopic reverberation mapping campaigns with the superb and densely sampled Rubin photometry in the deep drilling fields to perform improved reverberation mapping of the broadline region to measure black hole masses for these same objects that we're studying in the multi-wavelength sense. We, of course, are interested in looking at the variability of the dwarf galaxies in the optical. A lot of interesting science to be done there. We're interested in optimizing AGN color and variability selection. Once we have the Rubin data, we can analyze these superb deep drilling field data. We can downsample the deep field data to be just like a general AGN sky, a general Rubin sky region. And then we can optimize AGN selection for the full main survey. And we hope to generate tens of millions of AGN with the Rubin data by getting that optimization done as well as possible. Of course, we're interested in transient supermassive black hole phenomena, tidal disruption events, changing look AGNs, jet flares from blazars, micro-lensing events, so on. We're interested, of course, in binary supermassive black hole searches, and we're interested in improving the constraints still further upon supermassive black hole growth. There's a lot of exciting things to do once Rubin switches on, and we're laying the groundwork to make these types of studies possible right now. And also, just to mention that in these deep drilling fields, of course, it's not just the Rubin data that are coming. There's tremendous amounts of other fantastic multi-wavelength data that are coming in these same fields, ranging from, in this top row, a large number of spectroscopic surveys, some of which are ongoing or mostly completed. Sloan, for example, is already doing spectroscopic reverberation mapping in these fields to measure black hole masses. Devils has gotten large numbers of spectra. This is an Australian project. And then soon, extremely powerful spectrographs, such as moons, PFS, foremost waves, and foremost tides, will be pounding the heck out of these fields and getting us huge numbers of excellent spectra. And then there also are excellent, deep optical data that are already available, already have been gathered. I've tried to get them, and they won't give them to me for whatever reason, from the Hawaii folks in the Hawaii 2.0 survey. There is also an extensive sort of sub-millimeter program with the Toltec instrument on the LNT. That would be very powerful for studying these objects at longer wavelengths. And then, of course, there also are superb radio surveys that are completed and ongoing, such as the excellent MIND data that we can use to do even further radio AGN studies and AGN selection. So there's a huge amount of multi-wavelength data coming, in addition to just the Rubin data. And combining all of these data sets together is where I think we'll get the most exciting science. And I'll stop there. Thank you. I'm happy to take any questions.
Thank you. Yeah. The floor is open for questions now.
Yes, please.
Do you have exactly when will be available?
From Rubin. Well, I have a date that is listed on a web page. Whether that's going to be the actual date, I mean, only deities or something know. But briefly, I will say, I mean, the nominal date, and maybe if there's an expert in the audience who's more up to date than me, maybe you know. My understanding is, according to the webpage, the current date for the observatory to be qualified for the full science survey to begin is around September 2025. So it's an exciting time for the Rubin Observatory right now. You know, I've been involved since 2005. It's been a 20-year haul. And so, yeah, 1 year looks actually, that's hardly any time at all. So it should be very exciting soon. And maybe you have an update there?
Yeah, data 51, which is based on the content data that we just
Yeah.
this fall, that comes out in June or July along with the event.
Yeah.
And the science validation surveys that we're going to take when we're commissioning LSST camp, those will come out roughly 6 months after the science validation ends and the white test survey starts, so expect that late spring.
Yeah, so that's the sort of time scale. So.
DR1, September 26th is the earliest.
Sorry, data preview, that's data preview.
DR1.
We call it data preview.
People really care.
Probably the end of 26.
Yeah, so it's crunch time now for us, yeah, so
Are
it's
you also
soon.
interested in alerts?
Pardon me?
The difference pipeline
Yes.
alerts, are you interested?
Oh, absolutely, yeah, we are.
So those start around February.
Yeah, that's absolutely, we're extremely interested in those, yes, yes. Any other questions? Yes, please.
So this is, you mentioned the monitoring two building fields. The Euclid field has relatively less.
Multi-wavelength data, yeah, that's right.
I think, Gordon, you're on the Roman
Yeah,
prime
Roman.
building committee, and that is the prime candidate for the.
Yeah, I mean,
That's something that you think about.
current plan would be to prove Roman time domain data, one of the fields would be Euclid field itself, where the overlap of the two LSST regions would go a little bit deeper and maybe be a target for prism.
But does this choice affect how you're going to follow up those fields, or you don't want that field to be
Well,
the choice?
basically, well, I mean, again, as I mentioned, we're not exactly rolling in cash. And so we are doing our honest best with whatever we can find to get ready. So just out of practical necessity. So I mean, I engaged in this work on the deep drilling fields, you know, a decade ago. And we've been crunching on it for a decade, long before Euclid Deep Field South has ever even selected. And so, you know, we have a decade's worth of work on those 4 fields built up pretty well. I don't have the resources, at least right now, and I don't have the time, because the Rubin data are coming, and I have to worry about that, to start chasing around yet another field. I mean, the time to tell me that was a decade ago, not now.
So your sense is that that field is less well prepared compared to the other.
At the moment, yes. I hope that can be improved, but that, to my understanding, that is certainly the situation right now. You know, as far as I know, the people at Penn State, my group, have done the best selection of AGNs, the best mining of the multi-wavelength data to characterize the AGNs. I'm not aware of any comparable AGN studies in the Euclid Deep Field South right now. It'd be a great thing for someone to go and do it, and I think you could do some, you know, relatively basic, shallow, you know, optical selection of AGNs quite straightforwardly in that field. But pushing the multi-wavelength data to the level that we've got in these other fields, that's not something you just knock off in a month or two. That's years of effort. Yeah. Yes.
This is great. Can you say a little bit more? I mean, I know you've gotten really great deep X-ray coverage
Yes.
of all these fields, but for like variable sources.
Yes.
I mean, it's just like the proposal system, you know, coordinating with XMM or putting in a bunch of Swift things. I mean, what do you think, how do you think this will kind of work for the, you know, maybe some of the really variable sources you identify, or maybe in the deep fields, they're just really faint.
To follow them up with X-rays. With X-rays.
Did you see them
right.
change a lot?
Yeah, well, okay, so yeah, I think you're basically on the right track there. It's going to be very challenging. And as you say, we're pushing quite deep here in the deep drilling field. A mission like Swift, which is well characterized and chasing around things, is just too bright in general to do a good job at it. You know, so you know, ideally you would want a mission like you know, well, like StarX, which we recently put forward, but unfortunately was not selected to do that.
Access.
Or Axis, that's going to be a while. I mean, you know, Axis would be starting operations while Rubin is well along its way, and even, you know, its first decade might even be starting to wind down a bit by then. And so it's a ways away. So yeah, it's going to be a challenge. We did our best with StarX to try to give such a facility as confident as one could, and that's where we are. Yeah. Clearly, Chandra and XMM one people can put in time domain proposals for them, but their capability to respond to these things, as you know, is limited on short time scales.
Okay, well, let's move on and
Yeah,
thank
sure.
you.
Thanks.
Thank you. Okay, so let's hear about discovering black holes and AGN using machine learning.
Thank you. All right, so I'm going to give a 15-minute version of the 5-minute talk that my grad student Ash Karali gave on Monday. Basically just talking about plans that we have for doing AGN selection with machine learning. And I'll kind of just try to whip through this stuff and maybe have some time to actually discuss. So LSST by itself will discover something like 10 to 30 million AGNs. It will detect something like 300 million AGNs, but obscuration in host galaxy dilution is going to hinder our selection, and so we hope to recognize about 100 million of those AGNs at the end of the day. Some challenges: LSST will catalog about 40 billion sources. And our job is to figure out, which of those are the 100 million AGNs. And so a huge issue is that if we make a 1% error, then that's 400 million things that aren't AGNs that we have discovered. And so 99% is not good enough for your machine learning algorithms. Curse of dimensionality is going to be a huge issue. You can't just take 379 parameters and look for outliers in them. That doesn't work. The input data is very multimodal is the word used these days. So, there's numbers, there's different scales, there's text, there's images, and so on. We have to figure out how to deal with all that. And I mean, maybe the biggest thing in my mind is the training set is vastly not representative. And so we need some way to deal with the fact that the things that we are looking to discover are things that by and large we haven't discovered except for the 10,000 objects, Niel is talking about. So, traditional selection for AGNs and quasars sort of looks like this. You've got some color plot. You've got, blue things in the bottom left corner, red things in the upper right-hand corner. And we make some cuts in color space, and, they can be fairly complicated. And then you go off and take spectra of them, and you're happy if, 50% of the things that you took spectra of turn out to be the AGNs that you wanted to find. For LSST, we have much more data than that. So this is just highlighting two of the many variability parameters that we could look at and include in our selection. And so you can see, the stars and the quasars overlap, but they overlap hopefully in a different way than they overlapped for the colors. And when you can combine those together, you're going to hopefully do a better job of having a nice clean selection of your AGN sample. We can do the same thing with the astrometry, proper motion, things like that. And then as Niel was mentioning for the deep drilling fields in particular, we have data from other telescopes, right? So combine X-ray data, infrared data, and so on, and really help at least in the areas where we have those deep data sets to clean up our selection. Okay. I don't know why that's not... Okay. Well, I'll ignore that. I think this was basically one of the slides that Niel showed, just highlighting the different multi-wavelength data. So machine learning is the way we are going to have to do this. We can illustrate this a number of ways. Here I'm just showing a simple decision tree. You ask a series of questions. Is my object, static? Is it variable? Is it periodic? Is it non-periodic? And so on, and sort of follow your decision tree down and to do your classification. Like I said, though, we have lots and lots of different types of data, and one of the things that we really need to do is basically look at all at once. So astronomers have a sort of bad tendency to only look at the things that they know, So, people that do optical selection do optical selection. People that do variability. People that do X-ray do X-ray. We really need a new generation of people that are doing all of those things simultaneously. And so these are just all of the parameters that we need to try to figure out how to deal with simultaneously. And that, sort of kitchen sink approach is perfect for machine learning. So, when I teach my machine learning class for astronomers and physicists, we use scikit-learn. I want to emphasize it is not a machine learning tool. You can't actually do real machine learning with it. It's a toy for you to learn how to do machine learning. And so you need to pair, with basically computer scientists that can help deal with algorithms that are going to deal with 40 billion objects and so on. And one of the things that we've learned from like the plastic competition and so on is that at the end of the day we're probably going to need sort of ensemble methods. Averaging of different approaches. There's not going to be like one AGN selection algorithm for all of LSST, right? So we're going to do different things in the deep drilling fields, different things for wide, fast, deep, different thing for low Z, different thing for high Z, different thing for type 2s, and so on. Okay, so I want to highlight sort of one possible approach because I think it's a good starting point for people to think about how machine learning works and how we can sort of leverage the lack of good training data that we have. And so the way I am thinking about this problem is this. So I want to start with an unsupervised process to literally cluster every single one of those 40 billion sources, right? So the 40 billion sources basically become our training data. And then with that clustering, and I'll illustrate this in a second, we're going to use transfer learning and a normal supervised process to actually extract our AGNs, right? And so I'll illustrate that here, right? So we don't have the training set that we want to identify the AGNs. But what you can do is some kind of process where you basically say, okay, I'm going to clump all 40 billion of my sources into groups, so 3 sort of groups here. I don't know what those are, but at some level I don't care at this point. I'm just going to say these things look alike, these things look alike, and these things look alike over here. All right, so that's our unsupervised process. And then one of the ways that we can do this is through something called an autoencoder, a particular type of neural network, where what we do here is, so in this case we're taking input data with 784 features, and we're funneling that down into a bottleneck that has, say, 30 features. So basically we're saying, okay, yes, you've measured 784 floating point numbers for this object, but that's not the intrinsic dimensionality of the data, right? So luminous quasars are probably a two parameter sequence, right? So the amount of sort of information that we need to identify all AGNs from everything else is maybe 10 or 30 dimensional or so on. So you funnel your 784 down to something like 30, and then you've done a good job capturing the data space if when you take those 30, you can basically recreate the data that you started with in the first place. And so that's how an autoencoder works. And so then the idea here is this. So you're doing this on all of your training data, right? And the way I think of it is that's literally all 40 billion sources. And then, so you're figuring out what's the algorithm for taking my 784 dimensional parameter space down to 30. And then you're going to do that for the tiny fraction of objects that you actually have the answer for. And then hook that up to a traditional supervised classification algorithm, whether it be a random forest or what have you, right? Okay, and so now you've got basically these objects classified in using the parameters for all of the objects. And so now you go back to your original clumps and you say, okay, well, I didn't know before, but based on my the objects that I do have the answer to, these are AGNs, these are stars, those are galaxies, and so on, right? And so I'm dramatically oversimplifying this, right? So the state of the art here is nicely illustrated by this paper led by Đorđe Šabić in Serbia from 2023. So as Niel mentioned, the AGN Science Collaboration ran a data challenge in 2021. Basically what we did is we took some SDSS data, stripe 82, some time domain, and so on, and converted that as closely as possible to the LSST data model. We put that on the SciServer platform being run by the folks at Johns Hopkins, and had a Docker image basically with all the software that people needed, and so on. And so asked people to like find AGNs, do PhotoZ, do whatever. This is the closest thing that we have to LSST stuff right now. And so that paper exists. I want to highlight in particular Georgia Savic's quote solution to the problem used a variational autoencoder, a little more sophisticated version of what I just showed. I was actually talking to the Hopkins folks this morning, and what we would really like to do is extend that data set. So it was mostly known AGNs and variable stars. And so the problem is, when people would sort of run their algorithm and get 99% completeness and efficiency and sort of pat themselves on the back, it's sort of like, well, okay, there's not normal stars and galaxies in there, right? So you actually haven't done as well as you'd like. The simplest thing that we could do there really is to take the entire Sloan database, recognize that about 50% of Sloan sources are junk, diffraction spikes, and so on. And so if you look at the flags, you can basically get rid of those. But if we basically take the entire Sloan database, get rid of the object with bag flags, translate that to the LSST data model, we could basically update the data challenge. And then an enhanced goal would be to add the Cosmos data, as Niel said, that one of the fields where we really have a significant amount of multi-wavelength data. So certainly, take a look at this, and if anybody's interested, we would like to do an update of this. As Niel said, there's no funding for it, so it's basically whatever somebody can do in their spare time. But the more people that come up to me and say, hey, yeah, I would do something with that, the more likely it is that it'll actually happen. And then I really want to highlight work that's being done by Paula Sanchez-Sayas. She and her team are much more interested in broker-based science, whereas I'm really more focused on what we can do with the data release data. But this particular paper I want to highlight. So this is ostensibly about finding changing look AGNs, but I think this is, the approach that she takes in this paper is really exactly what we should be using for a template for data release-based selection. So she's using this variational autoencoder. It kind of just makes a lot of sense how they have that structure set up. And I guess the point I would really make is more of the activity that is going on to prep for LSST is sort of happening in broker space. And that's great, but we're not going to identify all the AGNs as variable sources all the time because they need to be 5 sigma deviations from the template and so on. And so there's going to be things that we can do with the brokers, and there's going to be things that make much more sense to do with the data releases. And I think that we need to probably do a better job of sort of learning from each other. And in particular, Paula's work, I think, is a great place to start for those that are sort of more interested in the data releases. And at some point, she's going to present this work to the AGN Science Collaboration classification subgroup. Okay, so that's pretty much all I wanted to say. Niel already showed these pictures about the most recent meetings, and I'll just leave this up, but I wanted to really, more importantly, leave a few minutes for people to talk about any of this stuff. So, thanks.
Thank you. Great talk. The floor is open for questions.
Matthew.
2 comments. Firstly, Shimon Nakanoshi, my postdoc, has just finished creating a ZTF AGN catalog using deep learning and transformers.
Great.
That's about 5 million AGN based on variability and Gaia and Ys, and there's a larger catalog which is about 55 million AGN candidates. So that'll be coming out, well, it should be going to archive probably in the next month or so.
Fantastic.
So look out for that. The second thing is, you're talking about putting 40 billion light curves through the full thing, That's great if you have all the data you need for your 40 billion sources. So this is not a thing we'll do in year 1 or maybe even in year 5. So there's a structured timeline that needs to be done of a successive AGN catalog potentially, whereby you feel you have enough information to be able to do the discrimination to the degree that you want to do to create the data set you want at that particular time.
Yeah, I think, ideally, we would have the training set that we want, and we would have one algorithm that we would start running on day 1 and then never change that in 10 years, because at some level, when you do surveys, that's what you would rather do. In this case, I don't think we have the luxury. So we're going to do something that we know is not complete, not ideal.
But I mean, if you're after
change that constantly, right?
But if you're after variability features, some of those things only converge when you've got 5 years worth of data or something, if you're trying to do fits to get those features before you put them into the...
Sure. I think one thing that we can do, though, is maybe take advantage of Cosmos, which is going to have the full tenure depth in the first 3 years, right? And at least, learn what we can from that, right?
I'm just curious, you said that 30 represented the features just to reduce the dimensionality. I mean, is that 30 is the real number from your experience, or you might?
No, I mean, that's just an example from the MNIST digits, data set. But I mean, like I said, I would argue luminous quasars are a 2-parameter sequence, right? Maybe 2.5 or something. And okay, so now you've got to add in low luminosity AGNs and things like that, and then you've got to select them from stars and galaxies. So, I mean, it's not going to be less than a 10 parameter.
I guess my question is it easy or straightforward to have some feeling, okay, I got to stop, let's say 10, 15, or whatever, 20, or people have to still, play with that number, see how it changes or...
No, so I mean, that's a really good question. So I think one of the issues that we have is that you do need some domain knowledge here. You can't just send a computer scientist to go off and do your dimensionality reduction for you. You need some knowledge of what it is that you're looking at, right? And so no, definitely not easy.
Look at Tachibana et al. 2020. We already did autoencoders on Catalina AGN.
Yeah.
And the space was 16 in the latent space, because we found that less than 16 didn't work.
Yeah.
And that was for just...
So I guess a question, so one of the things that Paula, I know, is trying to do is just subclassify things, right? So at some level, I don't care if an object is a YSO or a supernova 1A or whatever. I just want to know it's not an AGN.
Yeah.
Now, to the extent that it helps you to know that it's not an AGN because you know it's a YSO or a supernova 1A, that makes your life easier. But at some level, like the level of detail that some of the people that are working on broker stuff are going into is, I don't think we care, right? And so maybe we get away with a little less than 16, but yeah.
For your selections in the main survey, in terms of optimizing your selection methodology, do you plan to rely mainly upon the drilling field or upon models or upon a mix of both? What is your thinking?
I mean, I think the DDS have to be our primary training set. Yeah.
So maybe it is not very directly related, but when I was in Taiwan, we have a summer project collaborate with the scientists who use the YOLO to do the machine learning to identify the elliptic galaxies and the spiral galaxies. And we found feeding the galaxy too, and we found if we testing data is also from galaxy too, well, it's much good predictions, but when we change the philosophy of facilities from all the different, telescope, the identification, correct rate just dropped. So is there any similar analysis in your Asian machine learning functions?
I mean, maybe we should probably get going, but why don't we can talk offline about that, yeah.
We can certainly, thank you for the question, and we can certainly take it offline. Okay, we are going to hear from Yasaman, and she's going to talk to us about reverberation mapping using photometric and spectroscopic observations. I'm going to find your
I have a keynote if it works. If not,
Is it this one?
there should be. Yeah, that's the one. Yep.
Okay, do you have a PDF here? Interesting. How do you read? Okay, it's no, not downloaded yet. Take it away. Thank you.
Hi everybody, my name is Yasaman Homayouni, and today I want to talk about some of the prospects of photometric and spectroscopic reverberation mapping using a Rubin LSST. But before I go into the detail, I'm not sure if everybody knows the reverberation mapping, so I'm going to go into a little bit of detail here and give you some background. So we know that black hole mass is correlated with some of the properties of the host galaxy, including the mass of the central bulge and also galaxy's stellar mass. So the bigger the mass of the black hole, the bigger the central bulge mass, and similar trend is observed for the galaxy's stellar mass. But one thing stands out here is that when you do these kind of studies, a lot of the measurements are limited by the large error bar on the mass, which practically covers about 1 order of magnitude. Through better studies of black hole mass, we can do other things besides the measurement of the mass, which includes better understanding of the mass inflow to the black hole, better study of the broadline region, and also physics of accretion, and also black hole galaxy coevolution. And we can also study some of these properties as a function of redshift, so we can do we can sort of study AGN evolution. So in general, when you want to study the inner regions, you have this very compact region that you cannot really resolve. But there are, of course, some exceptions. There are the case of the event horizon telescopes that you can, it's only practically possible for these two sources. And there's also cases of study of the resolving the broadline region, this gas surrounding the black hole, through the gravity observations. There are more measurements than what I'm showing here, but you get the idea that you can use these measurements to resolve the structure of the rapidly moving gas around the black hole. But these are a handful of targets, so we need better tools to do this kind of measurement. So here comes the technique of reverberation mapping, also known as echo mapping, where the idea here is that the AGN environment is prone to rapid short-term changes. So when the central region, the driving continuum from the central region hits the different components, different components react differently. They reprocess the light, and after some time delay, you can see the reprocessed light. So you can see the direct emission from the continuum, but you can also see the reprocessed emission in red, but there's a time delay between them. And through that, we can get an estimate of the size. So beyond 100 megaparsec, this is the only tool we can use to resolve this, resolve the physical distances in and near the black hole. So this technique, by probing these physical distances around the black hole, we can get an estimate of the virial product, where the radius of the broadline region is identified by this time delay measurement through reverberation mapping. The velocity is obtained from the velocity width of the broad emission lines that is observed in the gas. And we can get a virial product, and there's a component called F, the fudge factor, that includes all the information that we do not know about the rotation, the inflow and outflow, all the orbital structure that we don't know. So in principle, this technique can be done for any source. It could be low luminosity, high luminosity, low redshift, high redshift. But in practice, up until about a decade ago, this has been done for about 60 AGNs. And these are the mass that has been measured about 10 years ago. Most of them were in H beta, more prominent line, doable in UV, doable in optical. There are a few lines based on the MG2 emission line, and there are a couple in carbon-4. One of the main byproducts of reverberation mapping is a scaling relation between the black hole mass or the radius of the broadline region in H beta and the continuum luminosity. So what you see here is the scaling relation, and these are all the masses that were so far measured by about 10 years ago that were lying nicely on the scaling relation. But when you overplot all of these over in all the quasars that are measured through SDSS, thousands of quasars are measured through SDSS, you can see that they probe a pretty narrow range in parameter space. And it seems like we need to do a better job at identifying what sources we want to target in this sample, diversifying our sources going into a broader range of parameter space. So the SDSS-RM, the Sloan Digital Sky Survey reverberation mapping campaign, and its continuation as a part of SDSS-5 Black Hole Mapper program, was started back in 2014 with the goal to diversify the sample of quasars that were using SDSS multi-object spectroscopy observations to get an estimate of the black hole mass. Through the selection of based on magnitude, we expanded the parameter space in redshift and luminosity. The campaign is probing all the way to redshift of 4.5, and it's going to continue all the way to 2026 as part of the Black Hole Mapper program. We are a team of about 15 people. These are some of the key people you see here. The main goal of the campaign is to do lag measurement and get an estimate of the black hole mass through reverberation mapping, but we also do some ancillary science, such as study of the black hole, the host of these galaxies, also studies of the accretion disk, broad absorption line studies, and also radius luminosity relation. In this work, in this slide, I want to highlight the work done by one of our students. She's in the job market, Meg Davis. She's going to give a talk tomorrow in the same session on binary supermassive black holes. So I encourage you to check out her talk tomorrow. So when the campaign began in 2014, this was our prediction that we had for all the detection of lag that we had. This is from year one of observation, and there's addition based on the pan-stars of observations. And we added, after a decade later, this is all the measurements that we've done, which added about 300 more measurements than what we existed in the literature. In terms of the radius luminosity relation, this is the scaling relation that we had, and you can see how the addition of all the lag measurements have expanded the parameter space, both in the eigenvector run plane and also in the radius luminosity relation. And you can see how it's all kind of offset. So the scaling relation that we used to know is not a good description. So the LSST deep drilling field observations would add about 900 more epochs into the SDSS-5 Black Hole Mapper program. This would accompany the photometric observations that will be done through SDSS-5. And the end goal here is that we end up targeting about 1,500 quasars, and the end goal is here to detect about 800 reliable lags. And this is what you see here is the open symbols are all the masses that we would get from the combination of SDSS-5 and LSST observations, and the field symbols are all the already existing measurements through 7 years of observations. So far, let me give you a quick summary. So we're using reverberation mapping to use physical sizes, to use light echoes to probe physical sizes near the supermassive black holes. For this, we need multi-epoch observations. These are campaigns that are done through months and years. SDSS-RM has already tripled the sample of existing data on black hole mass measurements, and it's a huge expansion in terms of parameter space. But there's one issue here. There's the cosmological time dilation effect that affects the time measurements through a factor of 1 plus z because of the redshift. So when you want to do reverberation mapping with targets beyond redshift of 3, it's going to be pretty much impossible. So we need more extended campaign, but how do we do this? So now I'm going to shift a little bit to talk about something slightly different, but I promise to come back to this. caveat that I just described. So we can use, similar to what I described about reverberation mapping in the broadline region, we can use the same principle to study the accretion disk. By targeting the inner region and the outer region of the accretion disk, we can get an estimate of the black hole accretion disk size and obtain a disk size measurement. This work was done with the SDSS-RM first year of data, and you can see the previous campaign that already had disk measurements, and you can see how the SDSS-RM has expanded the number of targets with reliable disk measurements. What we saw in this study is that we see a lot more diversity than what we expected. You can see the gray disk measurements from before, and you can see how all the disk sizes are very different than what you would expect from the average. The average is a good description, but there's a lot more diversity than we thought, and we might think that it might be relevant to factors such as black hole spin or radiative efficiency. In this work, we also connected the accretion disk measurements because we had this kind of a sample of about 100 reliable disk measurements. We could do a statistical modeling on the parameters about the connection to black hole mass and accretion rate. So we did a nonlinear regression. We applied nonlinear regression to connect to disk size. This is the disk size normalization, and also black hole mass, which is based on the Shakir-Saniev's SS73 expectation. It's actually a pretty good match. And instead of accretion rate, we connected to the luminosity as the observable quantity. And all of this seems fine, but there seems to be a factor of 2 days that is maybe connected to any kind of missing physics that we have. This could be, again, connected to the spin, radiative efficiency, and goes back to all the diversity that we see on the accretion disk that we cannot explain. So how does this all connect to what I described about the issue with the redshift? So it turns out that when you, in the Shakir-Saniev model, when you try to connect to the redshift, this is very weakly dependent on redshift. And accretion disks are generally shorter. So if a broadline lag is about 100 days, accretion disk is somewhere about 10 days. So you can, using LSST measurement, you can first off target the accretion disks more in a broader sense. And you can also connect to the disks that are already measured in the SDSS-RM. So if we can use the overlap of the existing disk measurements in SDSS-RM, cross-match targets, and try to identify what parameters contribute to the diversity that we saw in the SDSS-RM, disk measurements, we could come up with some kind of mass scaling relation that would describe all those diversity, but it could also mitigate the redshift issue. And then through more masses from SDSS-5 and LSST combination, we could recalibrate that scaling relation and kind of go into up to redshift of 4 or 5 with knowing that this does not rely on spectroscopy anymore. Photometry is much cheaper, and it's also weakly dependent on redshift. This is my last slide. I think I'm right on time. With this the aim here is just to use all the knowledge that we have from black hole mass measurements and accretion disk measurements from SDSS-RM, trying to recalibrate come up with this mass scaling relation and expand the parameter space of come up with a black hole mass estimator that would go up to a redshift of 5. This would again mitigate the issue of targets in a billion years after the beginning of the universe, and they are more massive than what we expect, and the current mass scaling relation tends to overestimate masses by about an order of magnitude. So I'm going to end you with a summary, and happy to take any questions.
Thank you. Are there questions for you? While they are thinking, I have a quick one. So, how long the observations? What's the duration of observations typically you need for the reverberation studies?
You mean the baseline of observation?
You observe a source for a certain period of time to match the variability between the and
right. So the work that I showed here was about from 6 months of observations. Typically, it depends on the targets we have. If you're looking for more specific type observation, like for example with Hubble, we test what we want and we usually ask for the limit that we have. But the longer the better. We did try to see if we can get accuracy disk measurements through multi-years of data, because what I showed here was from SDSSRM, these have 6 month gap within them. So that really affects, that gap really affects, because accuracy disk measurements are.
It seems like with the first 1 year of Ruby
Yeah.
data, there will be a lot of interesting studies.
Yes, absolutely.
Well, thank you. Are there more questions? Okay, then let's move on to the next talk, and we are going to hear about radio surveys and their synergies with the Rubin observations. So I would like to invite Mark, who is going to this. I think I need to download this one. There is some issue with PDF thing. Okay, sorry, over to you.
Okay, thanks. So yes, I just wanted to give a quick talk about what we can do, synergies with the radio surveys that are happening in the LSST footprint over the next few years, and why radio is interesting. I mean, radio, as you most know, of course, radio emission is characteristic of energetic cosmic systems, not just AGN, but also supernovae, star-forming galaxies, and also more nearby objects, such as active stars, planetary nebulae, protostars, X-ray binaries. The nice planetary nebula there on the right. The top is a VLA sky survey observation, and the bottom is the optical, showing that we're getting to the point now where we're sensitive and high enough resolution to really start to match some optical images. And then now these radio surveys, even the wide field ones, are now sensitive enough to detect both the traditional radio loud AGN and a lot of radio quiet or radio intermediate AGN as well. And now we're also exploring the time domains. So there are a lot of surveys like the VLA Sky Survey and the RAC survey in the south that are having multiple epochs, so you can compare the variability in the optical and the radio and try and help understand about accretion mechanisms and their variability. So I just wanted to point out some radio surveys that are going to be particularly useful in the next few years. So the VLA Sky Survey, this is the highest resolution survey. It has 3 epochs. We just finished observing the 3rd epoch. We're going to do one further pass of half the sky next winter, which will just about overlap with the start of Rubin observations. We tried to get more time, but we didn't manage it. But it's definitely going to be a useful reference for sure. And that gives you data over the whole sky down to minus 40 degrees. That's still like a 70% overlap or something with LSST. The one that I think a lot of you will be using is the ASCAP survey, the RAC survey. This is with the Australian ASCAP telescope. It's lower resolution than VLAS and lower frequency. And I think they're just going to repeat cycling through some frequencies fairly close together, so they're not so far apart that they're, you wouldn't be able to find transients and that sort of thing. And that's over the whole of the southern hemisphere. And then the VAST survey is actually a targeted time domain survey, more targeted on specific fields with a range of field sizes and cadences, which I won't try and explain here, but you can go to their website and that has the details. And then in the future, the EMU survey is going to be a sort of RACS on steroids. It's going to be the whole southern survey, but much deeper than RACS. That'll be very useful for finding star-forming galaxies as well as AGN. DSA 2000 is a northern telescope. It will be based in Nevada, but I'm sure there'll be some overlap with the LSST images. This is going to be a very powerful telescope. It's a 3 arcsecond resolution, dedicated survey telescope, doing 3 to 4 passes of the sky per year, and possibly starting as early as 2028. So I think, for the AGN science collaboration, I think this is a really good the radio synergies are really good. I just sort of highlighted what people are actually using the VLA Sky Survey, because that's what I happen to have the numbers on. And definitely AGN, radio galaxies, and time domain are dominating our authors right now. So these things are very relevant. So what other things can we do with the AGN continuum? Identification of radio loud, radio intermediate quasars. We now have a detection of an object at redshift 7, so we can go all the way out there with even the VLAS, relatively shallow VLAS survey. Ultra-high redshift radio galaxies and quasars should be identifiable as dropouts in LSST bands, so that'll be an exciting field. One thing that's new for radio surveys is that we now can have spectral index information across a band. So we go, for example, in VLAS, we go from 2 to 4 gigahertz, and you can see on the top left image there's a continuum image. It's a bit unclear what it is. It's a sort of blobby radio image. But when you look at the spectral index map, you can see the blue area there near the center, a little offset to the right, is where it's flat spectrum, and that tells you where the optical identification is, where the actual galaxy is, and you can see on the bottom image there's a galaxy actually there in the Pan-STARRS data. So spectral studies can also help us identify young objects, because they tend to have peaked spectra or flat spectra, and distinguish, as I say, coarse lobes or hotspots. And there's another thing that I think could be quite exciting, is that when you combine the optical and the radio data, you can search for places where the radio jet and the AGN may have interacted with galaxy. So very few cases of these are known right now, but I think there's going to be a lot more discovered when we start combining the optical and the radio, resolved radio data. There's sort of hints of it on this sort here. There's that galaxy on the bottom right that's right next to the jet. You need spectroscopic confirmation to be sure, of course, but I think this could be a very interesting thing for the future. And then there's also statistical host galaxy properties. I mean, trying to understand why some radio loud quasars are radio loud and some are radio quiet. I had a summer student a few years ago now, right during the pandemic, who looked at the properties of host galaxies in the Pan-STARRS and Legacy survey, so pretty shallow. We could only get out to about redshift 0.2. With LSST, of course, we'll be able to do much better and be much more sensitive to low brightness emission from tidal features and things like that. Do a more reliable job of classifying the host galaxies as a function of radio and optical luminosity. And another nice thing, the paper came out just the other day that I was seeing that this is a nice study trying to find wandering black holes or off-center black holes in dwarf galaxies. Of course, radio loud dwarf galaxies are pretty rare, but if you've got 1 million sources in VLAS and many millions of dwarf galaxies from LSST, you can start to look statistically at some of these rare cases where there's potentially offset black holes in dwarfs. And that tells you something about the formation mechanism of black holes in the early universe, because they all started off in small galaxies. Another thing that we're very excited about is trying to correlate the radio and optical variability. So Christina Nyland found a nice sample of quasars that increased substantially in radio emission between the 1990s, the first radio survey, and the first epoch of VLAS, basically changing from radio quiet to radio loud. We're starting to look at these within the time domain of VLAS now, where we can correlate with DTF as well. And we're finding a variety of behaviors, but I think this will be a very important thing to look at in the future. How is the change from radio quiet to radio loud to radio quiet to radio loud associated with a change in accretion state, for example? You might be able to see that with a big enough sample. One very cool thing which is, I think, coming up as well is looking at polarimetry. So all these radio surveys, again, are coming with polarimetric information as well as spectral index information. Basically, you're looking at the density of the magnetic ionic medium as it rotates the plane of polarization of the radio waves as it passes through them. And so you can use this to trace things like cluster densities and essentially the cosmic web. So this is a nice example of the Fornax clusters. This is some Craig Anderson's work with ASCAP. And then you see on the left there, there's the Fornax cluster itself, and the X-ray contours there. And then on the bottom right, you see those little white contours of the Fornax A radio galaxy, famous nearby radio galaxy, and that patch of high Faraday rotation medium here is probably some sort of front where the main Fornax cluster is colliding with the group associated with the Fornax radio galaxy. So combining that with photometric redshift information from LSST and clustering information is going to be very exciting, I think. Gives us a real chance to trace some interesting structures. Niel's already talked about the DDF, so I won't talk much more about them, except to say, yes, there's a lot of much deeper radio data than we'll get from the VLAS or RAC surveys already there. The Atlas survey, the Mighty survey with Meerkat now has data release 1 out, so they've done a little more data collection and imaging. And there's also an upcoming S-band survey, a 3 gigahertz survey, which one of my REU students led. There's a problem with CDFS. There's a one Jansky source, which is sort of the evil bright source that we're all trying to get rid of, and it's causing some delays both for Mighty and for our survey, but we're working on figuring that source out and getting it cleaned out. So yeah, just to summarize, there's a lot of radio data that will overlap both spatially and temporally with the start of LSST, VLA Sky Survey, ASCAP surveys, deep surveys in the DDFs. There's a lot of synergies, I think, that will teach us about, for example, the nature of radio loudness, particularly exploring this time domain aspect, I think is going to be very exciting. And I'd like to issue a plea. So VLAS, is going to be done. I think the ASCAP, it's not clear how long the ASCAP surveys are going to go. I think this is really good as a community. It'd be really nice to get together and make a case for future wide area radio surveys that are going to be more contemporaneous with LSST, especially in the Southern Hemisphere, or that can go into the Southern Hemisphere. And there might be opportunities for this, for example, in the VLA, NG-VLA transition period. The VLA will be operating in some simplified mode, so it might be useful for some surveys. So thanks, everyone.
So for the Eden survey you mentioned, should be very complementary to that. I guess you mentioned it's just getting started now or soon. What's the time scale over which will cover the significant part of the movement?
I think they're at about 20% now, and I'm not sure what their observing rate is, but I think it will be a few years before they finish. But it will be within, it will be within the Rubin lifetime for sure.
And that's at the copper Eden depth, not just racks.
Yeah, that is full depth, yeah.
And I have,
Similarly, about the other survey that you mentioned, the 2000 survey?
Yeah, DSA2.
You said it was going to take 3 or 4 passes for the survey, but how many years are you planning to operate at that cadence?
So right now, I think DSA 2000 is planned for 5 years, but the lifetime of the telescope, they say, will be like 20 years. So if it gets funding to continue, then it will be able to continue for longer, yeah.
Oh, sorry, yeah. Why? I need a minute. Go ahead with the questions, please.
so just another quick question. So people have tried to define a hardness intensity diagram analog for AGNs. Typically involves looking at something like the ultraviolet luminosity versus alpha OX, which is a kind of similar parameter to what stables for the black hole binary in such in our galaxy. So my question, I guess, is while you probably don't have alpha OX for these objects over long because those are the X-ray, you almost surely do have ultraviolet luminosities going back a year. So these island objects change in optical or ultraviolet luminosity if you look back at the 1950s archival data versus today.
Certainly haven't looked back that far. Our initial look has not shown much. But yeah, looking back to like 50 years would be interesting, yeah. Times. Yeah, no, that's a good idea. Interesting.
Could you say anything about the timescale for release of the LSS products? I guess
So-
there's a lot of computing involved in it.
Yeah, so the quick look products, which are actually good enough for a lot of science you'll want to do, are available already for the 3D POCs. And we are working on these, particularly the spectral index stuff and the polarimetry, so things like that. Spectral index map, those are coming out more slowly, yeah. So we've only got about 20% of the sky for that right now. But we are working on it, yes, it is a lot of computing. We've got a challenge from our observatory director to finish within 3 years, we'll see whether we can do that.
Okay, with that, let's thank Mark, and I welcome the next speaker. We are going to hear about the high redshift quasars from Do you have a PDF of this? Yeah, I'm just trying to download and it's not working. Okay, it's working now. It's working. Okay, while it's downloading, we are going to hear about high redshift quasars, observations using Rubin data and synergies with other surveys, and it's taking a while. It's better to download the PDF. Do you have the PDF over here or no? Okay, that's okay. It's slow at the moment. Okay, it's getting there. Okay, over to.
Okay, now you're done.
Okay,
Right.
over to you.
Okay, so we're going to have high-redshift quasars. This is mostly based on Wei Long Ti's thesis work, which he didn't have time to show yesterday, so we can ask him questions. The quasar that we're talking about are basically quasars at epoch reionization, roughly speaking, a redshift higher than 5.5 or so. The starting point of these gains were from the early days of SDSS 25 years ago, when you start using color selection to find them. And over the last 2 decades, a succession of newer surveys, PanSTARRS, DES, DECALS, HSC, and other infrared-based surveys are expanding the parameter space to fainter objects, higher redshift. Now we are at highest redshift about 7.5 or so, with about 10 quasars which are higher than 7. And altogether, they are a few hundred quasars at redshift 5.5 or so, sort of epoch reionization now. So that's overall, the community has built up a very large sample of these objects over the years. So the question is how much further you can push with narrow of LST and Rubin and Euclid, and what you can learn from them. This is a plot of all the few hundred quasar spectra that we put them together. You can see, of course, they're just lemma alpha marching to the infrared wavelengths now. So finally, lemma alpha become an infrared line to the highest redshift. Of course, each line is one quasar. You see not only lemma alpha, but also strongest broad lines remain to be very strong with very little evolution, go to the highest redshift. The other thing that you see here is on the blue side of the lemma alpha emission line. on the blue side of landmark emission line, the strong intergalactic medium absorption tells you you're basically getting into the epoch of ionization now. And the reason that we like these objects is really they are probing how supermassive black holes, the very massive ones at least, the most luminous ones, are impacting and being impacted by early galaxy formation, all the way from the seeding of the black hole that you see from looking at their X-ray and UV emission to the host galaxy property that people begin to look at with LSST and ALMA, to the largest scale, as I showed before, how the strong radiative feedback is impacting cosmic ionization. This is a spectrum of the highest redshift quasar, and quasar in this case, sort of classic luminous object, not the little red dots and stuff, such that people begin to discover using JWST these days. This is the highest redshift quasar still today. Probably will not be the highest redshift I predict in the next year or so, but it's a redshift 7.6. This one is an interesting object, not only the highest redshift one, but also actually the highest redshift broad absorption line quasar. You can see strong carbon-4 and silicon-4 absorption in the spectrum. Tells you their feedback process is probably from wind coming from the central engine already at those redshift. JWST observation begin to show these objects do have impact on their host galaxies through ionized winds as well, extending to a few kiloparsec scale. And of course, this spectra allow you to measure the black hole mass with scaling relation. You can do reverberation mapping with this kind of redshift and luminosity, of course. And this particular object is estimated to be about 1 billion solar mass black hole. Not only this object, but now we have a large sample of objects that have these mostly magnesium-2 based black hole masses. Now the JWST can give you a H-beta based black hole mass, sort of similar answer. They are mostly accreting at very close to that integration, with mass somewhere between 10 to the 8 to 10 to 10 solar masses, the object we've discovered. So of course, if you combine the black hole mass with adding accretion, then that's a typical thing that people like to show, that in order to grow them to be billion solar masses with redshift 7 or 7.5, you need them to grow really early and really fast. That is beginning to constrain or put pressure on the on what kind of seed black hole that you can get, and that's why people are interested whether they're implying intermediate mass black holes rather than sort of a stellar evolution process that we give the initial seed of these objects. Of course, the objects that we are observing at those redshift are the most massive ones. They're not going to grow much further than this. So we're looking at an end product. In order to actually answer the seed problem, you need to go to higher redshift, and you probably need to go to lower luminosity to catch sort of in between the end product and the initial seed. And that's why we're trying to push towards higher redshift. Actually, because the density of quasars is dropping so quickly, you can begin to ask the question of sort of when the first quasar, the first luminous quasar that in the observable universe appear, and you just extrapolate the number density to higher redshift. The answer is for sort of your typical luminous SDSS-like quasars, about 9. Then you're running out of volume of the universe or density to, so that's about it. That's about the highest redshift that we can get, and the question is how to get there. The answer, of course, is a combination of Rubin, Euclid, and Raman, which give you the wavelength coverage and the depths for the photometric selection. That principle you can get to redshift 9 or 10 or so with the sensitivity and an area that you have. And that is sort of the goal of the work is trying to make some predictions of how many things, especially with in this paper, combining Rubin and Raman, it's going to get you. Just a side note about Euclid's data look fantastic. Even though without the very deep LSST Rubin observation to give you the optical wavelengths, people already begin to find quasars, and the data look good. The spectroscopic actually look better than I thought, so that's why I said maybe in a year or so we'll talk about even higher redshift. The problem of finding these objects is basically because they're rare, so the contamination is high. In Gordon, we're talking about 99% purity. We're not going to be 9. We're going to be 1% purity in some cases. The sort of standard thing that we were able to do at redshift 6 also for spectroscopic observations is sort of the older 30-50% success rate, which was already very good for us. But it's down to really a few percent at redshift 7 and for the fainter magnitude. And the reason is on the right-hand side, it's because the number of objects that are dropping out in an optical band that are not quasars have a density few order of magnitude higher than the redshift 7 quasars we're talking about. With a broadband, the left-hand side plot shows the quasar spectrum compared to various L and T dwarfs. With a broadband photometry, it's very hard to tell the difference, especially if your dropout band in the optical is not deep enough. So the thing that we try to do is, because there's not much of a training set to speak of, these are tested territories in both redshift and luminosity, we have to rely on sort of basic synthesize or simulate not only the quasar population, which is probably easier, but the contaminant population as well, and then try to work on whether we can select things a little bit more efficiently. You do not have a lot of features to choose from. They're just a bunch of colors. So the strategy that Weilong was proposing is actually at bright end, the color dropout technique is just sort of okay for the depths of Rubin plus and Roman. But at the faint end, you have to work a little bit harder to do that, essentially using the Bayesian model comparison technique that people have been developing for finding these high-risk quasars, essentially just try to figure out the quasar density compared to the surface density of the contaminant populations, galaxies, and like redshift 1 or 2 galaxies and cool dwarfs to try to cut out the parameter space to make the selection more efficient at the some sacrifice of completeness. So that's the proposal, and this is what he showed, the sort of the predicted yield of quasars. Of course, that number critically based on the things we don't know. That is the quasar luminosity function, how they evolve. That's what we're trying to find out. But you can look at the number of objects that we're talking about a redshift higher than 6.5 or so by combining Rubin and Roman and Euclid. Basically, the answer is a few hundred. And in this case, Euclid is sort of 50,000 square degrees of area, of course, shallower. And Roman give you the infrared photometry of 3,000 square degrees, but a couple of magnitude fainter than Euclid. So depending on exactly what is the faint and slope of the luminosity function, essentially the yield of these two surveys give you roughly the same number of quasars. Of course, one of them is a shallower, brighter sample. The other is a fainter and smaller area sample. But we're talking about hundreds of objects at redshift higher than 7, and hopefully get a few objects at redshift 9 or so. And I think that is probably, as I mentioned earlier, that's probably all there is for luminous, as far as luminous quasar is concerned, luminous type 1 quasar is concerned. And we played about how complete the sample is and what kind of success rate we're talking about. The overall completeness is actually quite high. You're not losing a lot of objects no matter how you cut it, just because the dropouts essentially select all of them. But the success rate drops pretty quickly when you go to essentially 24 magnitude and lower. We're talking about 10% also completeness, even with the BMC selection at magnitude about 25. So that is going to be the challenge, both because of the purity is low, and also because that means you need more spectroscopic time. So we tried proper motion, of course, it turned out not going to be terribly helpful to select out cool dwarf contaminants. For Rubin, it's just not going to go deep enough, because Rubin is mostly dropping out in these bands. And even for Roman, with a few years of baseline, we're talking about brighter objects that you may be able to improve it by a factor of 2 or so by getting rid of the cool dwarfs. But of course, proper motion doesn't help you when the fainter magnitude, most of the contaminants are higher galaxies. The biggest worry is really how do you actually identify these objects with spectroscopy. They're really at the limit of current facilities when you go to 23, 24 magnitude doing sort of far optical near-infrared spectroscopy. So that's probably have to rely on things like ELT to do it. That's a simulation of what a redshift 10 sort of low luminosity quasar would look like with GMT. And the bottom panel is a redshift 7.5 quasar spectrum coming from JWST. This is like 10 minutes exposure for the 1 to 2 micron band. So JWST for these objects is actually overkill. You just need a few minutes. The problem is you don't have, it's very hard to design a program and efficiently use the telescope at 4 minutes. Sort of in this no man's land, ground-based is very hard, space observations is too easy. So we are exploring things like the JWT survey mode, whether that's a more efficient way of at least to start doing spectroscopic selection to understand the contaminants. I think that's about it. So the summary is quasar selection going to be hard when you go to looking for the first quasars, but in principle, we'll be able to find hundreds of these objects and detect sort of the first generation quasars or redshift. 9 also, the most difficult thing for us, some challenge is how to do faint object spectroscopy at those redshifts. Thank you.
Thank you, John. Are there questions for you?
Just a naive question might be, but how the resolution help or does not help? If we don't have the Roman and Euclid, then Rubin alone.
Resolution, spatial resolution.
Yeah, spatial resolution.
There are point sources.
Helpful or the other way?
So for galaxies, it helps a little bit, but the objects that we're talking about, fairly compact galaxies and fairly faint objects, so not really. I think the spatial resolution for a space telescope is not, I mean, you really just need an infrared to do to detect the object rather than, the spatial resolution doesn't help very much.
There's some confusion, right? If you have the sources at a high redshift, the general is very compact, also galaxies.
Well, even the contaminants are fairly compact, so
Yeah,
it's not, when you have 1 arcsecond resolution is probably good enough. I don't think you're going to gain a lot more by the object being extended.
So
Most of the contaminants are point sources.
Are there no questions? Please go ahead.
My apologies, I mean, how much is variability going to be able to help? Sorry.
Well, I mean, for the fainter end, maybe, I mean, these are redshift 7, so 10 times slower varying, so I don't think we ever tried to do variability. They're both luminous and 1 plus Z is killing it, so.
But on the very wide field surveys, Euclid, the Roman, they're going to have multiple components.
Right, and I think the 10-year, the Fourier time scale, very few of them in the Fourier time scale has shown a lot of variability as long as I know for these objects. They're just too bright.
Yeah.
Thank you.
Okay, let's thank the speaker. Thank you very much. And the final talk is from Amy, and she's going to talk to us about AGN variability and learning about the disk structure using Rubin observations. I'm trying to. Okay, you will.
Just a second. Yep, I'm right there.
Thank you.
All right. Hi, everyone. I'm Amy Secunda. And yes, I'm going to be talking about probing accretion disk structure with Rubin using the primary tool that I use to study AGN disk structure, which is reverberation mapping. And so we just had a talk earlier on reverberation mapping. So, just really quickly, the way that discontinuum reverberation mapping works is you have some time-varying X-rays emitted from the corona or the region very close to the supermassive black hole. And some of these X-rays come straight towards us, but some of them move outwards along the disk where they are reprocessed by the disk based on the local disk temperature. And then they lead to kind of an echo of variability, first in the UV, then in the optical. And so because we know the light crossing time scale, we can calculate what the radial temperature profile and radial extent of AGN disks from this. And so I think now is really an excellent time for reverberation mapping for kind of 2 main reasons. First, because we have these new codes that let us do multi-wavelength radiation magnetohydrodynamic simulations of this reprocessing, so we can study reverberation mapping by simulating it self-consistently. And then the second is because of Rubin Observatory, which is why we're in this room today. But ironically, I'm going to actually talk more about these multi-wavelength radiation magnetohydrodynamic simulations, but also how they can be useful for preparing for Rubin. So because that's quite a mouthful, I'm just going to really quickly talk about what goes into these simulations and why they're kind of unique from most of the simulations and models that other people do of reverberation mapping, and why the physics that I'm capturing in these simulations are worth it, because they're very computationally expensive. And so first, the hydrodynamic part, right? The gas disk that reprocesses the X-ray into UV or optical is not some constant disk. It's evolving. That's why it's hydrodynamic. And so in these simulations, these are like the four main equations that are evolved in my simulations. In these simulations, the hydrodynamic part is the part that evolves the gas density, pressure, and energy. Second, we have the magneto part, and so this is the part that evolves the magnetic field, which is really important. I was talking to Gordon on Monday about how much does magnetic fields provide pressure support for AGN disks. If you believe the new Hopkins fire zoom-in simulations, it does all the pressure support. But even if that's not true, the magnetic fields drive the magnetorotational instability, which we think is what drives accretion in AGN disks, and it also drives turbulence. And so again, you don't have this static gas disk, you have this evolving gas disk. And so including these magnetic fields is really important in these simulations. Next, we have the radiation part, which is unique in these simulations because the radiative transfer is fully coupled to the MHD evolution through these source terms on the right side of the equation for radiation pressure and radiation energy. And so what this means is that the gas disk knows about the radiation and will evolve accordingly, and then vice versa, the radiation knows about the gas physics. And that self-consistency is really important. Actually, in the simulations I'm going to show, the radiation pressure and the radiation energy each play kind of their own role in setting the variability in AGN light curves. And then finally, kind of what the most novel part of my simulation is this multi-wavelength part, which is represented by those summations. So in most radiation MHD codes, they do something called gray radiation. So they integrate the radiation over all wavelengths of light. But if you're interested in reverberation mapping and seeing how high energy photons are reprocessed into lower energy photons, then you're going to need at least two different wavelength groups for your radiation in order to represent these two. And that's exactly what we do. So we have one wavelength group, that's the long wavelength group based on the local disk temperature. So in the case of these simulations, the UV. And then we have a second wavelength group, a short wavelength group, that we use to simulate time-varying X-rays that we inject into our simulation. And so we have our local disk temperature, long wavelength, our short wavelength X-rays, and then we can measure how the long wavelength flux leaves the simulation. So we can construct reprocessed UV light curve. And so here are some light curves from the simulations in my 2024 paper. In orange, I'm showing the X-ray light curve we inject into the simulation, which we model as a damped random walk. And in green is the actual results from the simulation, which is the reprocessed UV light curve that's emitted from the simulation. And so you can see by eye that they're only kind of moderately correlated. We find a Pearson R coefficient of 0.54. And the reason that these aren't more strongly correlated is because of the way we model the X-ray opacity. So in this simulation, we model the UV opacity using tabulated opacities from Opal. But for the X-ray opacity, we kind of just simply take the proper average of the scattering and the free opacity, which for X-ray photons means that we're completely scattering dominated. And so what happens here is that source term for energy doesn't really come into, for radiation energy, doesn't really come into play because there's no absorption. And so you don't get an energy transfer. You don't get, absorption heating from the X-ray to the UV. And so it doesn't know super well what's going on. But you do have that source of radiation pressure. And so the X-ray radiation exerts a pressure, an impact force on the gas that does translate some of the variability structure in the X-ray to the UV. And so you get these moderate correlations, but not a very strong correlation. And actually you can see that really clearly when you compare the temperature profile, the vertical temperature profile, in purple when we inject X-rays, and in blue when we don't inject any X-rays. And you can see that there's significant heating going on, right? Kind of in the outer regions of the disk, even though, again, there's no absorption. And this is this impact force that heats the gas disk. And what's interesting about this that we've been trying to think about a little bit is how does this impact the SED emitted from this region of the disk? Essentially, you're going to have a high energy tail to the photons in this SED, which means that you have higher energy photons at larger radii than you expect, which might be a hint of why we're finding these longer than anticipated lags that make the disk look larger than what we would predict. So the final thing I'll say is that these moderate correlations are interesting because there have been recent reverberation mapping campaigns with SWIFT that find only moderately correlated X-ray and UV optical light curves. And so if these AGN have scattering atmospheres, this could be a possible explanation for that. However, we also see lots of cases where the X-ray and UV optical are strongly correlated, and we'd like to be able to simulate that as well. And so what we do is we improve our X-ray opacity model by adding tabulated X-ray line opacities from the online software TOPS. So here I'm showing the opacity scaled by the scattering opacity as a function of photon energy for a couple different densities and temperatures based on these TOPS opacities. And you can see that even above our cutoff for X-ray photon energy of 1 keV, the opacity is several orders of magnitude greater than the scattering opacity, which means now we're going to get absorption, which takes us from this poor correlation to this really strong correlation. So all we've done here, it's the same injected X-ray light curve in orange. All we've done is change the X-ray opacity model. So no other changes, and now we're getting a correlation coefficient of 0.9. And what's great is now that we have well-correlated light curves, we can ask more questions about the reprocessing we're seeing in our simulations. For example, we can calculate the response function for the reprocessing of X-ray radiation into UV radiation, which is easy to do in our simulations because we have even cadence light curves, so we can fast Fourier transform them. And for a linear reprocessing model like is commonly used in reverberation mapping, in Fourier space, this is just a simple division problem. And so here I'm showing the response function as a function of time for our simulation output in green, and in black I'm showing our best fit log normal response function. We use a log normal response function because, again, it's similar to what's used in reverberation mapping campaigns. And what we find is that the mean of our best fit response function is 1.4 days, and the width is, 1.4 hours, importantly, and the width is 0.72 hours. And so this is very interesting because when we do reverberation mapping, the lag that we're measuring is the light travel time. But in our simulations, we're just directly injecting the X-ray, so there is zero light travel time. On the other hand, when you do reverberation mapping, it's pretty common to assume that the timescale for reprocessing is 0. And here we're finding about a couple of hours. And so not too worrying because for this simulation, for the AGN mass, you would expect the light travel time to be on the order of days. So adding a couple hours to that, no big deal, can't account for these 2 to 3 times longer lags that we've been detecting. But it's just an interesting point that, the reprocessing timescale isn't 0, and if this holds for lower mass AGN, this hour timescale could start to become significant. So, okay, the next thing we can do is we can check how well this response function fits our simulation data by taking our X-ray light curve, reprocessing it with our best fit log normal response function, and then comparing the PSD of its variability, shown in black here, with the PSD of the variability in the UV light curve emitted from our simulation, shown in green. And in the bottom panel, I'm showing the fractional error between the two. And you can see that at low frequencies, it's a decent fit, but at high frequencies, it overpredicts the amount of variability that's in our UV light curve. And so that just means that this log normal response function is not doing a good job capturing the smoothing of high frequency variability that the gas disk does. So I'll try and quickly go through this part, which is how robust is this result for different X-ray light curves. So for example, we've modeled our X-ray light curve so far as a damp random walk. What if instead we model the variability PSD as a power law? And these power laws here are kind of corresponding to typical power laws measured for X-ray AGN PSDs. And so here I'm showing, again, the injected X-ray light curve in orange, the reprocessed UV light curve in green for these two different power laws for the variability. And you can see that the correlation remains pretty high. It drops a little bit, but it's still well correlated light curves. And then we can look at these response functions. And now you see for these response functions, the time scale for reprocessing drops to about half an hour or less, which is good. Although interestingly, when we look at the power law, the shallower power law PSD, you can see that the width for the reprocessing becomes on the time scale of an hour. And this is really because you need to capture the fact that when you have a shallower PSD, you're going to have more high frequency variability that is not going to be able to drive variability in the UV light curve. So there's just more smoothing that needs to be done. And you can see this again, kind of when we do the same thing as before, we reprocess the X-ray light curves with our best fit log normal response functions, and we compare the variability in those modeled light curves with our now simulated reprocessed UV light curve. And again, I'm showing the fractional error on the bottom, and you can see that for both cases, it underpredicts the amount of low frequency variability, which is probably because there's intrinsic variability in these UV light curves, so the X-rays aren't driving all of the low frequency variability. And then for the steeper power law, it's over predicting the amount of high frequency variability, which again is a smoothing thing. And so this is to suggest that, these log normal response functions are okay fits, but if you really want to be exact, you may need a higher order reprocessing model instead of just a linear reprocessing model where, you have a reprocessing model that isn't constant as a function of frequency, because it does change. So then the last thing that I'll talk about is what happens if we take the same damp random walk light curve, but we decrease the flux by a factor of 4. So here is a run we did with just the same X-ray light curve, but only has a quarter of the flux. And you can see now that the reprocessed UV light curve in green is not very well correlated. We only find a correlation coefficient of 0.21. And so again, because we've found in reverberation mapping campaigns weakly correlated X-ray and UV optical, maybe this is a potential explanation because X-ray luminosity in quasars is not consistent, and so it may be that this is a potential explanation. And I'll just show here that the reason it happens in our simulation is because the UV PSD, which I show in green, compared to the X-ray PSD, which I show in orange, has more variability at low to moderate frequencies. And so essentially the intrinsic variability is the main driver of variability in this case, which leads to this poor correlation. I'm actually showing in gray the PSD of the variability from our run where we don't even inject any X-rays. And you can see that even at moderate frequencies, even that run has more variability. So the intrinsic variability is just stronger when we decrease the flux. And so that brings me to my conclusion and the title of my new paper out on the archive yesterday. You can get continuum reverberation mapping in AGN disks, but only with sufficient X-ray luminosity and low albedo. And I'll also say that UV light curves have intrinsic variability that comes from these fluctuations in the gas disk. And I have a QR code for a GitHub where I put some mock light curves. And I really encourage people who are using their different techniques to do reverberation mapping to, test them out on these mock light curves, because there aren't a lot of mock light curves out there that include intrinsic variability. And I don't know if there are any that include intrinsic variability that's self-consistently calculated. And so I think it's really important to include this because I think it does change the answer. So thank you.
Thank you. Neil.
This is just something of perhaps my general interest. So if I'm understanding you correctly, you're mainly taking X-rays and just injecting them in a separate term. How close are these numerical simulations to being able to actually calculate the X-ray corona in a self-consistent manner so that it isn't just a magical term that's kind of imposed from the outside?
Yeah, I mean, that's certainly the dream.
Yeah.
Currently, I'm doing what's called shearing box simulations. So they're local approximations. And so we're not able to at all calculate like propagating fluctuations because we have periodic boundary conditions.
Aside from your personal work,
Yes.
more broadly, has
Yes.
anyone successfully calculated from first principles what the alpha OX should be?
Yes.
And
So
what the luminosity dependence of that should be?
So yeah, so there are global simulations. Most of the global simulations only go out to about 50 RG because they're just so expensive. And so, there aren't many there are no truly global simulations that get all the way to the ISCO that go out into the UV emitting region, say. But I do know there are people who are trying to calculate how fluctuations propagate there and trying to calculate the impact that has on the corona, and the variability in the corona. So I can probably point you to, I don't know if the paper's out yet, so I don't know if I can point you to it, but I know people who are trying to work on this, yes.
Are people able to calculate the base level of the X-ray emission, and do they get it right compared to observations without cheating and adding fudge factors?
Yeah, again, this paper I'm thinking of is like probably the one that's most likely going to be able to do that. Trying to think of, all right, because there are a lot of people doing, GRMHD of the inner region, including radiative transfer, but I think, a lot of them are focused on low luminosity kind of to match EHT results. And so once you get into like a quasar regime, I'm not as sure if they're out there. But yeah, let me think about it.
Okay. Oh, go ahead, please.
Okay, because you're modeling on MHD, so it means the magnetic field is in your calculation. So is it possible to observe on something like a VOA, the polarization and constrain your modeling?
Yeah, I mean, we haven't thought about that. It's possible. I mean, again, there's been a lot of thought of how can we constrain kind of these Hopkins fire simulations and, how can we relate that to observables because it's quite unusual what they're finding. So can we rule it out? Because it should look different. So, I mean, that's a question. But I don't know specifically with that, yeah.
So, and if you said this number already, sorry, but for these simulations, and maybe this is something you have on your GitHub, how long does it take to run, and what kind of, do you get the output, how much detail do you get on what the algorithm is doing internally?
Yes, so in terms of what do we get as output, whatever you want to get as output. So, I didn't show a lot of plots, but we output the disk structure so we can study things like that. We specifically at the highest cadence output the light curves because that's the thing we're most interested in. So, I think we go all the way down to 10 to the minus 4 days, something like that in outputting the light curve. At that point you're getting at numerical errors, and so it's, looking at that high cadence is not as useful. But then in terms of how long they take to run, they're pretty expensive. So, we get about 15 days of light curve per day, a little less, about 10 days of light curve per day. But, we have about 1,000-day light curves now for in this most recent paper. So, so 100 days. So anyway,
Okay, well, let's thank Amy and all the speakers.